Tonight, we're going to explore one of the most profound mysteries in all of science. A story that begins 13.8 billion years ago, in the first fraction of a second after the universe was born, when conditions were so extreme that the laws of physics themselves were barely holding together. A story about atoms, the building blocks of everything you have ever touched, seen, tasted, or breathed. And a story about how scientists spent decades convinced they understood where those atoms came from, only to discover the universe had been hiding secrets they never anticipated. Two elements, hydrogen and helium, make up 99% of all visible matter in the cosmos. Everything else, every carbon atom in your body, every iron atom in your blood, every oxygen atom in the air your lungs are drawing right now, accounts for just 1% of everything, and we now know exactly where that 1% came from. Stars. Those heavier elements were forged in stellar furnaces and scattered by supernovae, assembled into the molecular clouds that became our solar system. The story of the heavy elements is well understood and it is spectacular. But the origin of hydrogen and helium, the first atoms, the oldest matter in existence, that story turned out to be far stranger, far more violent, and far more precise than anyone predicted. Here is something remarkable to hold in your mind for the next hour. The hydrogen atom in a glass of water on your kitchen table has a proton at its nucleus that has existed since the universe was approximately 1 second old. That proton was present when the first stars were born. It was present when the Milky Way formed. It was present when our sun ignited. It was cycling through the early oceans of Earth when life first emerged. And it is here now, in your water, having passed through an unimaginable chain of events stretching across 13.8 billion years. The atom itself is ancient beyond comprehension, and we are only now beginning to understand all the secrets it carries. By the end of tonight, you're going to understand how the universe cooked its first atoms in the 3 minutes after the Big Bang. You're going to learn why the precise ratio of hydrogen to helium is one of the most powerful clues in all of cosmology. You're going to discover why the universe should have made equal amounts of matter and antimatter, and why it didn't, and why that single fact was the reason anything exists at all. And you're going to understand 7 discoveries about the first atoms that forced scientists to completely rethink what they thought they knew. Before we get into it, if you love exploring the deep history of the cosmos as much as we do, take a second to like the video or subscribe. It's a small thing, but it makes a genuine difference in helping this channel reach more people who are curious about the universe. Now, let's begin. The year is 1964. A pair of radio astronomers named Arno Penzias and Robert Wilson are working at Bell Labs in New Jersey. They're trying to use a massive horn-shaped antenna to study radio waves from the outer regions of our galaxy. But there's a problem. No matter where they point the antenna, no matter what time of day or year they take measurements, there's a persistent background hiss of microwave radiation coming from every direction in the sky with almost exactly equal intensity. They check everything. They calibrate the instrument. They look for interference from nearby cities. They check the antenna for flaws. They even find a pair of pigeons nesting inside the horn and remove them, cleaning out what they politely describe in their notes as a white dielectric material, which is to say pigeon droppings. Nothing eliminates the hiss. It's everywhere. It's constant. It's real. What Penzias and Wilson had stumbled onto was the most important astronomical discovery of the 20th century. They had detected the afterglow of the Big Bang itself, the cosmic microwave background radiation, light left over from a moment 380,000 years after the universe was born, when conditions finally cooled enough for electrons to combine with protons and form the first stable atoms. Before that moment, the universe was so hot that atoms couldn't hold together. The plasma was opaque, like the interior of a star. light couldn't travel freely. The moment atoms formed, the universe became transparent. Photons were released, and those photons have been traveling ever since, stretching as the universe expanded, redshifting from visible light to microwaves, cooling from thousands of degrees to just 2.7 degrees above absolute zero. They fill the entire sky uniformly, every direction, every moment, the oldest light that exists. Penzias and Wilson would win the Nobel Prize for Physics in 1978. But here's the thing. By 1964, scientists already had a prediction for what the cosmic microwave background should look like if it existed, and they had a prediction for something even more fundamental. They had a theory about exactly what the universe should have made in the first few minutes of its existence. They called it Big Bang Nucleosynthesis, and it was one of the most audacious theoretical predictions in the history of science. To understand what the first atoms are and where they came from, you have to understand what the universe looked like in its first moments, not its first years, not its first days, its first fractions of a second. At the moment of the Big Bang, the entire observable universe, everything you can see with the most powerful telescope ever built, was compressed into a space smaller than a proton. Temperature was effectively infinite. Density was effectively infinite. The laws of physics as we understand them break down at this moment. We don't have a theory that describes time zero, but within the first 10 to the negative 43rd seconds, an interval called Planck time, the universe began to expand and cool. This expansion wasn't like an explosion in space. Space itself was expanding. Everything was rushing away from everything else, not because things were moving through space, but because the space between them was growing. By the time the universe was 1 microsecond old, about 1/1,000,000th of a second, the temperature had dropped to about 10 trillion degrees Celsius. The universe was filled with a dense, hot plasma of quarks and gluons, the fundamental constituents of matter. Quarks are the particles that make up protons and neutrons. But at 10 trillion degrees, it's too hot for quarks to bind together. They exist freely in a quark-gluon plasma, a state of matter so extreme that it took physicists until the 1990s to figure out how to briefly recreate it in particle accelerators. At about 1 microsecond, something happens. The universe cools just enough for quarks to start combining. Quarks bind together in groups of 3 to form protons and neutrons. The quark-gluon plasma freezes into a hadron gas. The building blocks of atomic nuclei now exist. And here is where the story of the first atoms truly begins. For the next several seconds, protons and neutrons exist in a hot, dense soup, along with electrons, positrons, photons, and neutrinos. The temperature is still hundreds of billions of degrees. Nothing can stick together yet. Conditions are too violent, too energetic. Any nucleus that tries to form is immediately blasted apart by the intense radiation. But the universe keeps expanding. It keeps cooling, and as it cools, a critical transition begins. At about 1 second after the Big Bang, the temperature falls to roughly 10 billion degrees. This is still more than 1,000 times hotter than the center of the sun, but it's cool enough for a crucial reaction. Protons and neutrons are converting back and forth into each other through weak nuclear force interactions. A proton absorbs an antineutrino and becomes a neutron plus a positron. A neutron absorbs a neutrino and becomes a proton plus an electron. These reactions are happening constantly, keeping protons and neutrons in a specific ratio. Because neutrons are slightly more massive than protons, about 0.14% more massive, it costs slightly more energy to make a neutron than a proton. So at equilibrium, Protons are slightly more common. At 1 second after the Big Bang, there are about 7 protons for every neutron, a ratio of 7 to 1. Then something critical happens. At about 1 second, the universe has expanded and cooled enough that neutrinos stop interacting with matter effectively. The neutrino decoupling. From this moment on, neutrinos stream freely through space without affecting anything else. The conversion reactions between protons and neutrons slow dramatically and then stop. The ratio of protons to neutrons is now locked in at approximately 7 to 1. But there's a complication. Neutrons are unstable. Left alone, a free neutron decays into a proton, an electron, and an antineutrino with a half-life of about 10 minutes and 11 seconds. If nothing happens to the neutrons in the next few minutes, they will all decay and the universe will end up with nothing but hydrogen. No helium, no heavy elements of any kind. A cold, dark universe of pure hydrogen gas. Nothing interesting, no star, no planets, no you. What happens next is the most consequential 3 minutes in cosmic history. At about 100 seconds after the Big Bang, the universe has cooled to about 1 billion degrees. This is still 10 times hotter than the core of the sun, but it's cool enough for a new process to begin. For the first time, protons and neutrons can stick together and stay together long enough for nuclear reactions to proceed. This is Big Bang Nucleosynthesis, the forging of the first atomic nuclei in the fire of the newborn universe. It is the moment when the universe begins making structure, when the raw ingredients of chemistry, of biology, of stars and planets, and everything we know are assembled for the first time. The process starts simply. A proton and a neutron combine to form a deuteron, the nucleus of deuterium, also called heavy hydrogen. This first step is actually the bottleneck. Even though the temperature has dropped to 1 billion degrees, photons are still energetic enough to destroy deuterium almost as fast as it forms. Physicists call this the deuterium bottleneck. Nuclear reactions cannot proceed efficiently until enough deuterium survives to feed the next steps. Once deuterium survives in significant quantities, the reaction chain runs rapidly. Deuterium fuses with another proton to produce helium-3. 2 deuterium nuclei can fuse to produce helium-4 or tritium plus a proton. Helium-3 can fuse with a neutron to produce helium-4. The reactions run in parallel through multiple pathways, all of them converging on helium-4, the most stable light nucleus in existence. Its binding energy per nucleon is much higher than anything lighter, which means it releases more energy when formed and requires more energy to tear apart. Once a helium-4 nucleus forms, it tends to stay formed. The reaction chain runs fast. Within minutes, almost all the neutrons that exist are locked inside helium-4 nuclei. The helium nucleus is so stable, so tightly bound, that once a neutron gets incorporated into one, it stays there essentially forever. Remember the ratio: 7 protons for every neutron at decoupling. But some neutrons have decayed in the 100-second gap between decoupling and nucleosynthesis. By the time fusion begins, the ratio has shifted to approximately 7 protons for every neutron. Different calculations give slightly different values, and the exact ratio is one of the quantities that the precise measurement of the helium abundance constrains. The arithmetic is elegant. If you start with 14 protons and 2 neutrons, and almost all the neutrons end up in helium-4 nuclei, you get one helium-4 nucleus containing 2 protons and 2 neutrons, plus 12 leftover protons. Those 12 protons are hydrogen nuclei, so the final ratio is 1 helium nucleus for every 12 hydrogen nuclei by number, which corresponds to roughly 25% of the total mass being helium and 75% being hydrogen. And then the fusion stops, not because the reactions are completed, but because the universe expands and cools past the point where nuclear reactions can occur at meaningful rates. The temperature drops below about 30 million degrees, and the nuclear furnace switches off. The composition is locked in. Whatever hydrogen, helium, deuterium, helium-3, and lithium-7 exist at this moment, that is what the universe will have going forward, modified only slowly by stellar processing over billions of years. The Big Bang has done its nuclear chemistry. The verdict is 75% hydrogen and 25% helium, with traces of everything else. This prediction was made in the 1940s and 1950s by physicists including George Gamow, Ralph Alpher, and Robert Herman. They calculated that if the universe started hot and dense and expanded according to general relativity, the first 3 minutes of nuclear reactions should produce a universe that is approximately 75% hydrogen and 25% helium by mass, with tiny traces of deuterium, helium-3, and lithium-7. They called this prediction Big Bang Nucleosynthesis, and it was a bold, falsifiable, precise, quantitative prediction about what the oldest matter in the universe should look like. Here's what makes it remarkable. When astronomers actually went out and measured the helium abundance in the oldest, most primitive stars and gas clouds in the universe, stars with essentially no heavy elements, material that has been as unchanged as possible since the earliest times, they found 24 to 25% helium. Everywhere, every measurement, in every direction, in every galaxy they could observe. The prediction matched the observation to extraordinary precision. This is one of the great confirmations in the history of science, an observation that cannot be explained by stars alone. Stars do produce helium through nuclear fusion, but they've only had about 13.8 billion years to work. If you calculate how much helium all the stars in the universe could have made in that time, you get about 1 to 2% by mass, not 25%. The other 23 to 24% had to come from somewhere else, from a time before stars existed, from the Big Bang. But confirming the big picture was just the beginning. When scientists started measuring more carefully, when they looked at the fine details of the first atoms, at the precise abundances of deuterium and helium-3 and lithium-7, they found something deeply unsettling. The universe was hiding secrets, and those secrets forced them to revise almost everything they thought they understood. Discovery number 1. The universe made far more lithium-7 than it should have. Lithium-7 is the heaviest element produced in significant quantities during Big Bang nucleosynthesis. It has 3 protons and 4 neutrons. The standard model of nucleosynthesis predicts exactly how much lithium-7 the Big Bang should have made, based on the density of protons and neutrons at the time of nucleosynthesis, and the prediction is precise. Based on the cosmic microwave background measurements, which tell us the density of ordinary matter in the universe with extraordinary accuracy, models predict a specific ratio of lithium-7 to hydrogen atoms. When astronomers measure the lithium-7 abundance in old, metal-poor stars that formed from essentially pristine Big Bang material, they find a value that is 3 to 4 times lower than predicted. Not slightly lower, 3 to 4 times lower. This is the cosmological lithium problem, and it has been sitting in the data since the 1980s. Scientists have checked every measurement, systematically explored every possible error. The discrepancy is real. It is statistically significant. It has not gone away. There are several possible explanations, and none of them are fully satisfying. Lithium could have been destroyed inside the oldest stars by mixing processes that transport surface material down to hotter interior regions where nuclear reactions can consume it. Some studies support this idea. Others argue that the mixing is insufficient to explain the full discrepancy. Alternatively, the physics of Big Bang nucleosynthesis itself might be slightly wrong. There could be new particles or new interactions that slightly alter the nuclear reactions in the first few minutes. Some models involving dark matter particles or additional neutrino species can shift the predicted lithium abundance, though matching all the other observations simultaneously is extremely difficult. Or the measurements themselves might be systematically affected by something not yet understood about how lithium behaves in stellar atmospheres. What's remarkable is that this isn't a small effect. A factor of 3 to 4 is enormous by the standards of precision cosmology. The helium abundance matches to within a few percent. The deuterium abundance matches beautifully. The helium-3 abundance matches reasonably well. And then lithium-7 is off by a factor of 3. Something is wrong. Scientists don't know what. This is shocking discovery number 1. The first atoms didn't come out in exactly the ratios we predicted. The lithium problem is real, persistent, and unsolved. Discovery number 2. The universe contains far more matter than it should. This requires some background. In the earliest moments of the universe, before nucleosynthesis, before even quarks had formed into protons and neutrons, matter and antimatter were being created and destroyed in equal quantities. Photons, high-energy light, would spontaneously convert into particle-antiparticle pairs. An electron and a positron, a proton and an antiproton. Matter and antimatter created together, annihilating each other back into photons, recreating and annihilating continuously in thermal equilibrium. The laws of physics, as far as we can tell, treat matter and antimatter symmetrically. Create one, create the other in equal measure. The universe at its birth should have made exactly equal numbers of matter and antimatter particles. If that were true, what would happen as the universe cooled? At some point, photons would no longer have enough energy to spontaneously create new particle-antiparticle pairs. The annihilation reactions would continue, but creation would stop. Every matter particle would find an antimatter partner and annihilate. The result would be a universe containing nothing but photons, pure radiation. No protons, no neutrons, no electrons, no atoms, no matter of any kind. A universe made of pure light, empty of structure, incapable of forming stars, galaxies, planets, or life. A universe that existed briefly and then became an eternal sea of cooling photons. That is not the universe we live in. We live in a universe full of matter, galaxies, stars, planets, the atoms in your body. All of this matter exists because something, somewhere, in the first fraction of a second, broke the symmetry between matter and antimatter. For every billion antiprotons, there were 1,000,000,001 protons. For every billion positrons, 1,000,000,001 electrons. When the annihilations happened, the antimatter was used up. The 1 in a billion surplus of matter was left over, and that leftover matter is everything that exists today. Every atom in your body, every star in the night sky, every galaxy stretching to the edge of the observable universe. All of it descended from a 1 in a billion asymmetry in the matter-antimatter balance of the infant universe. This asymmetry is called baryogenesis, the generation of an excess of baryons, which include protons and neutrons over antibaryons. And the shocking thing is, we don't understand why it happened. We know it happened. The evidence is all around us. But the laws of physics as currently understood cannot explain an asymmetry this large. There is a quantity in particle physics called CP violation. It describes the degree to which matter and antimatter behave differently in certain interactions. We observe CP violation in the behavior of certain particles called kaons and B mesons. But the measured amount of CP CP violation in the standard model of particle physics is far too small to explain the observed matter-antimatter asymmetry. The actual asymmetry in our universe is roughly 1 billion times larger than what CP violation in the standard model can produce. Something else violated matter-antimatter symmetry in the early universe. Something we haven't discovered yet. Some new interaction, some new particle, some new process that operated at energies and temperatures we cannot yet recreate in our laboratories. The first atoms exist because of this unknown process. Without it, matter would have been perfectly balanced against antimatter. All of it would have annihilated, and nothing we call the universe would exist. This is shocking discovery number 2. The existence of any atoms at all requires an asymmetry between matter and antimatter that science cannot currently explain. The first atoms should not exist. The fact that they do reveals a gap in our understanding of fundamental physics. Discovery number 3. Something we cannot see. Something we call dark matter, shaped where the first atoms ended up. After the first atoms formed, about 380,000 years after the Big Bang, the universe became transparent. The cosmic microwave background radiation was released, and at that moment, the universe wasn't perfectly uniform. There were tiny fluctuations in density. Some regions were slightly denser than others, not by much. The variations were about 1 part in 100,000. But those tiny ripples in density were the seeds of everything that followed. The denser regions had stronger gravity. They attracted more matter. Over millions and then billions of years, gas fell into these denser regions. The gas compressed, heated, and eventually ignited as the first star. Stars gathered into clusters. Clusters merged into galaxies. Galaxies gathered into clusters of galaxies, into filaments, into the vast cosmic web that astronomers can map today. But here's the problem. If you try to build this structure, this cosmic web of galaxies and voids, using only the ordinary matter we can see, the hydrogen and helium atoms made in the Big Bang, the gravitational attraction isn't strong enough. The fluctuations in the cosmic microwave background are too small. Ordinary matter alone can't clump together fast enough under its own gravity to form the structures we see today, not in the time available. Think about what this means concretely. When astronomers map the universe at large scales, they find something astonishing. Matter is not spread uniformly. It is concentrated in thin sheets and filaments, the walls of what looks like a cosmic foam or sponge, with vast empty voids between them stretching hundreds of millions of light years across. This structure is called the cosmic web, and it was built by gravity working on the tiny density fluctuations present at the time of the cosmic microwave background. But the math doesn't work with only the matter we can see. If you simulate the universe using only ordinary matter, starting from the observed fluctuations in the CMB, you don't get the cosmic web. You get a universe that's too uniform. The clumping happens too slowly. The structures are too small. The voids are too shallow. Something is missing. Something else is providing the gravitational scaffolding. Something that doesn't emit light. Something that doesn't absorb light. Something that only interacts through gravity and possibly through the weak nuclear force. We call it dark matter, and there is approximately 5 times more of it than ordinary matter. The evidence for dark matter goes far beyond structure formation. When astronomers measure how fast galaxies rotate, they find something that violates Newtonian physics if only visible matter is present. Stars at the outer edges of galaxies orbit just as fast as stars near the center, sometimes faster. In a system where all the mass is concentrated near the center, like our solar system, outer orbits should be slower, following Kepler's laws exactly as the planets do. The anomalously flat rotation curves of galaxies can only be explained if there is a large halo of invisible matter surrounding each galaxy, providing extra gravitational pull at large distances. Gravitational lensing, the bending of light by mass, provides independent confirmation. When light from distant galaxies passes through a galaxy cluster on its way to us, it is deflected and distorted by the cluster's gravity. The degree of distortion tells us how much mass is present, and the mass inferred from lensing is always much larger than what the visible stars and gas could account for. The missing mass is dark matter. The hydrogen and helium atoms made in the Big Bang didn't spread out uniformly and then clump under their own gravity. Instead, they fell into gravitational wells that had already been carved out by dark matter, which was clumping independently and invisibly from the very beginning. The first atoms followed the dark matter. They fell into its halos. They formed the first stars and galaxies at the locations where dark matter had already concentrated. Without dark matter, the universe of hydrogen and helium atoms would be a nearly uniform fog, thin, featureless, incapable of forming star. The first atoms needed dark matter as a guide, a gravitational template, a cosmic scaffolding onto which ordinary matter could fall and condense. We don't know what dark matter is. We know it exists. From its gravitational effects, the rotation of galaxies, the bending of light around galaxy clusters, the large-scale structure of the cosmic web. But decades of laboratory searches for dark matter particles have found nothing. Every proposed candidate, from WIMP particles to axions to sterile neutrinos, remains undetected. Direct detection experiments buried miles underground to shield them from cosmic rays have found no signal. Collider experiments at the highest energies ever achieved have found no new particles with the right properties. Indirect detection experiments looking for gamma rays or positrons produced by dark matter annihilation have found hints but no confirmed signals. It is possible that dark matter is a single new type of particle interacting only weakly with ordinary matter. It is possible that it is a collection of different particles. It is possible that it is not a particle at all, but some modification of gravity on large scales. The debate continues. The search continues. And the first atoms continue to reveal the influence of this invisible substance simply by being where they are. This is shocking discovery number 3. The first atoms were shaped and guided by dark matter, a substance that constitutes 85% of all matter in the universe, and whose fundamental nature remains completely unknown. Discovery number 4. The universe tore itself apart even as the first atoms were forming, and something we cannot explain is still driving that tearing. When the universe was young, gravity dominated. The early cosmos was dense enough that gravity was the primary force shaping the large-scale behavior. You might expect that over time, as the universe expanded, gravity would gradually slow the expansion. The universe should be decelerating, growing, but growing more slowly as time passes. In 1998, 2 independent teams of astronomers, The High-Z Supernova Search Team and the Supernova Cosmology Project were using a particular kind of exploding star called a Type 1a supernova to measure the expansion rate of the universe. Type 1a supernova are extraordinarily useful for this purpose because they have a consistent intrinsic brightness. By comparing how bright they appear to how bright they actually are, you can calculate exactly how far away they are. And by measuring how much the light from these supernovae has been redshifted by the universe's expansion, you can determine how fast the universe was expanding at different points in its history. Both teams found the same thing. The expansion of the universe is not slowing down. It is speeding up. The universe is accelerating. Something is pushing space apart with increasing force. Something that doesn't dilute as the universe expands. Something with what physicists describe as negative pressure, a kind of anti-gravity. We call it dark energy, and it makes up approximately 68% of all the energy content of the universe. Ordinary matter and dark matter together account for only about 32%. The first atoms exist in a universe that is dominated by something they have no significant interaction with. A mysterious energy that fills space itself and drives the universe toward an ever faster expansion that will eventually carry distant galaxies beyond the observable horizon, spreading matter thinner and thinner into a cold, dark void. We don't know what dark energy is. The simplest explanation is that it's a property of space itself, a cosmological constant, an intrinsic energy density of the vacuum. But when physicists calculate what the energy density of the quantum vacuum should be based on our understanding of quantum field theory, they get a value that is roughly 120 orders of magnitude, a 1 followed by 120 zeros, larger than the observed value of dark energy. This is considered the worst prediction in the history of physics. The actual dark energy is almost incomprehensibly smaller than theoretical predictions suggest it should be. Something must be suppressing the vacuum energy to an extraordinary degree. What that mechanism is, we have no idea. The first atoms were born into a universe that dark energy is currently tearing apart in a process whose ultimate cause remains the deepest open question in all of theoretical physics. This is shocking discovery number 4. The atoms born in the Big Bang inhabit a universe that is 68% dark energy, a substance that cannot be identified, measured directly, or explained from first principles. Discovery number 5. The first atoms weren't the first attempt at making matter. The universe tried before and failed, producing relics from an earlier era that should have been catastrophic. In the first tiny fractions of a second after the Big Bang, the universe went through a series of phase transitions as it cooled. These transitions are analogous to water freezing into ice or steam condensing into liquid. As temperature drops through critical thresholds, the structure of matter and the behavior of forces change abruptly. In one of these very early transitions, around 10 to the negative 35 seconds after the Big Bang, theorists predict that topological defects should have formed in the fabric of space-time itself. These defects arise wherever regions of space that went through the phase transition independently meet each other at incompatible angles. Depending on the nature of the transition, these defects can take the form of cosmic strings, domain walls, or magnetic monopoles. Magnetic monopoles are particularly problematic. Unlike ordinary magnets, which always have both a north and south pole, magnetic monopoles would be single magnetic charges, either north or south alone. They are predicted by essentially every grand unified theory, the class of theories that attempt to combine the strong nuclear force, the weak nuclear force, and electromagnetism into a single unified framework. And they should be extraordinarily heavy, roughly 10 to the 16th giga-electron volts, which is a quadrillion times heavier than a proton. If magnetic monopoles were produced in the quantities that theory predicts, one for every volume of space, roughly the size of a proton at the time of their creation, then by now, after 13.8 billion years of expansion, there should be roughly one magnetic monopole per cubic meter throughout the universe. That's an enormous density. Magnetic monopoles would dominate the mass of the universe. Gravity would have halted the expansion long ago. The universe would have recollapsed in a big crunch within a few million years. That didn't happen. We live in a 13.8 billion-year-old expanding universe. Therefore, either magnetic monopoles don't exist, or something reduced their abundance by an enormous factor. The proposed solution to this problem and several other related puzzles is cosmic inflation. A period of extraordinarily rapid exponential expansion in the first tiny fraction of a second after the Big Bang, probably around 10 to the negative 35 seconds, during which the observable universe expanded by a factor of at least 10 to the 26 in an unimaginably brief interval. Inflation solves the monopole problem by diluting any pre-existing monopoles across a volume so vast that our entire observable universe, stretching 46 billion light-years in every direction, descended from a region so small that it would contain essentially zero monopoles by chance. The exponential expansion simply spread everything out beyond detection. Inflation also explains two other puzzles. It explains why the cosmic microwave background is so uniform in temperature, differing by less than 1 part in 100,000 in every direction. Without inflation, regions of the sky on opposite sides of the universe would never have been in causal contact. They could never have exchanged heat. They shouldn't be the same temperature. Inflation solves this by saying all those distant regions expanded from the same tiny, thermally equilibrated patch. And inflation explains why the universe is geometrically flat. The spatial geometry of the universe could in principle be positively curved like the surface of a sphere or negatively curved like a saddle. But observations show it is flat to extraordinary precision. Inflation explains this by taking any initial curvature and stretching it smooth, just as a balloon looks flat when inflated to enormous size. But here is the uncomfortable truth. Despite inflation's success in solving multiple problems simultaneously, we don't actually know whether inflation happened. We don't know what drove it. We don't know which version of inflation among the hundreds of theoretical models proposed is correct. We have no direct observational confirmation. The first atoms exist in a universe shaped by inflation, if inflation is real. And the evidence for inflation is strong, but not conclusive. The search for direct confirmation continues. This is shocking discovery number 5. The very first atoms emerged from a universe that had possibly just undergone an episode of violent exponential expansion that smoothed out catastrophic relics from an earlier era. but the mechanism behind that expansion and the nature of the relics it erased remain subjects of active scientific debate. Discovery number 6. The first atoms of hydrogen and helium are not really ancient. The protons and neutrons inside them are ancient. But the electrons orbiting them were captured only after 380,000 years, and those same electrons get shared and exchanged and rearranged endlessly in chemical reactions. The atoms as discrete, stable structures are actually younger than we might think. And the real story of what makes atoms ancient is the story of their nuclei. Here's something that almost nobody thinks about. When we say the first atoms formed 380,000 years after the Big Bang, what we mean specifically is that protons captured electrons and formed neutral hydrogen atoms for the first time. This moment is called recombination, a slightly misleading term since the electrons were combining with protons for the first time rather than recombining. The neutral atoms could no longer efficiently scatter photons. The universe became transparent and the cosmic microwave background radiation streamed freely. But the nuclei themselves, the protons and helium nuclei, formed much earlier during nucleosynthesis in the first 3 minutes. And the protons were themselves assembled from quarks at about 1 microsecond. And those quarks emerged from the quark-gluon plasma at the beginning. The proton at the center of every hydrogen atom in your body is 13.8 billion years old. It was forged in the fire of the Big Bang. It has existed continuously since the first second of the universe. If it is in a hydrogen atom, it has been capturing and releasing electrons, participating in chemical reactions, being incorporated into molecules, joining and leaving stars, cycling through the interstellar medium for billions of years before it ended up in you. The nucleus of each helium atom in the universe was assembled in the first 3 minutes in a furnace of billion-degree plasma through nuclear reactions that we can now recreate in particle physics experiments and that we can calculate from first principles. And then it traveled, essentially unchanged, through 13.8 billion years of cosmic history, until it arrived in whatever context it is now, whether in the sun's core, in the interstellar medium, or in a birthday balloon. This stability is astonishing. A proton, as far as we can measure, is completely stable. Experiments searching for proton decay, the spontaneous disintegration of a proton into lighter particles, have found no evidence of it occurring. The current lower bound on the proton lifetime is about 10 to the 34 years. That's 10 trillion times the current age of the universe. Some theories predict proton decay should occur, particularly grand unified theories. If protons do decay, then ultimately all ordinary matter in the universe is temporary. All the hydrogen and helium made in the Big Bang will eventually vanish, but on timescales so incomprehensibly long that it makes the current age of the universe look like a fleeting instant. The first atoms are survivors, ancient beyond comprehension, assembled in conditions we can barely describe, persisting through the entire history of the cosmos, and possibly permanent on any timescale that matters. This is shocking discovery number 6. The protons that form the nuclei of the first atoms are among the most stable and ancient objects in existence, persisting essentially unchanged since the first second of the universe. And the processes that created them and that theoretically could destroy them reveal deep tensions between our most successful theories of particle physics. Discovery number 7. The first atoms reveal that the universe we can see, all the atoms, all the dark matter, all the dark energy, may be only a tiny fraction of a vastly larger reality. This is perhaps the most dramatic implication of all the discoveries made by studying the first atoms. When scientists analyze the cosmic microwave background with instruments like the WMAP satellite and the Planck satellite, they can extract extraordinarily precise information about the content and geometry of the universe. They can measure the density of ordinary atoms, the density of dark matter, the density of dark energy, the total curvature of space. And what they find is that the universe is flat. The total energy density equals, to extraordinary precision, the critical density required for flat spatial geometry. This flatness, as we discussed, is naturally explained by inflation. But inflation has a dramatic consequence. In virtually all inflationary models, inflation doesn't happen everywhere simultaneously and then stop. It happens in different regions of space at different times. Quantum fluctuations during the inflationary period constantly seed new inflationary domains. Inflation becomes eternal in the sense that globally it never really ends. It stops in some regions, producing universes like ours. But other regions keep inflating, and those regions spawn their own stopped bubbles, their own universes. This leads to the concept of the multiverse, an eternally inflating meta-universe within which our observable cosmos is a single bubble, one among an effectively infinite number of bubble universes, each with its own properties. In some, the laws of physics might be slightly different. The strength of gravity might be different. The mass of the electron might be different. The strength of the strong nuclear force might be different. In most of those universes, atoms as we know them wouldn't exist if you change the mass ratio between the up quark and down quark slightly. Protons and neutrons would have different masses, and Big Bang Nucleosynthesis would produce a completely different mix of elements. Change the strength of the electromagnetic force and electron orbits would be different. Chemistry would be impossible. Change the strength of the strong nuclear force, and nuclei, as we know them, wouldn't be stable. Our universe appears to be extraordinarily finely tuned for the existence of atoms, chemistry, stars, and ultimately life. The physical constants sit in a narrow range that permits atoms to exist and be interesting. This fine-tuning was one of the great puzzles of cosmology. Why these values? Why not others? The multiverse offers one answer. If there are effectively infinite universes, each with randomly selected physical constants, then we should not be surprised to find ourselves in one where atoms are stable and chemistry works. We couldn't exist in any other kind. We only observe the universe we're in, and we're in this one because the alternatives don't permit observers. But the multiverse remains deeply controversial. It is, in the strict sense, not testable by direct observation. We cannot see other bubble universes. We cannot measure their physical constants. We cannot confirm that they exist. The first atoms, the simplest atoms, hydrogen and helium, may therefore be evidence of a multiverse. Their existence in a universe finely tuned to permit them either reflects extraordinary cosmic luck, a purposeful design, or the inevitable result of observer selection in an infinite ensemble of universes. The measurement of the cosmic microwave background, the study of nucleosynthesis, the precise determination of atomic abundances, all of this observational work that confirms the standard model of cosmology, also forces us to confront this uncomfortable frontier. This is shocking. Discovery number 7. The first atoms, by confirming the standard cosmological model so precisely, also confirm the inflationary cosmology that leads to the prediction of an eternal multiverse, a structure so vast and so strange that it challenges our most basic assumptions about what science can and cannot say about reality. Understanding where the first atoms came from requires understanding the instruments and experiments that let us trace their history. Unlike the Voyager spacecraft, which directly flew through the environments they were measuring, the study of the first atoms is done remotely and indirectly, often through signals that have traveled billions of light years and billions of years to reach us. It requires some of the most sophisticated instruments humans have ever built, and some of the most careful and painstaking analysis in all of science. The cosmic microwave background is the central tool. The Planck satellite, operated by the European Space Agency and fully operational between 2009 and 2013, mapped the temperature fluctuations in this ancient radiation with extraordinary precision. The CMB temperature map is a snapshot of the universe at 380,000 years after the Big Bang. It shows the seeds from which all large-scale structure grew, and encoded within it is information about the density of ordinary baryonic matter, the density of dark matter, the geometry of the universe, the amplitude of primordial fluctuations, and much more. The precision is staggering. Planck measured temperature variations of about 1 part in 100,000 across the sky. The map has been analyzed in extraordinary detail, decomposed into its component frequencies using spherical harmonics, producing what's called the CMB power spectrum. The shape of this power spectrum, the pattern of peaks and troughs at different angular scales, encodes the physics of the early universe in a form that can be extracted with careful analysis. Each peak in the power spectrum corresponds to a specific physical effect. The first peak tells us about the geometry of the universe, confirming flatness. The second peak is sensitive to the ratio of ordinary matter to dark matter. The third peak constrains other cosmological parameters. The overall pattern is a fingerprint of the early universe, and the fingerprint matches the predictions of standard Big Bang cosmology, including Big Bang nucleosynthesis, with remarkable precision. The CMB power spectrum is one of the most precise confirmations of a theoretical framework in all of science. When you see a graph of the CMB power spectrum with the theoretical prediction overlaid, with the model and the data tracking each other almost perfectly across multiple peaks, you are looking at one of the greatest achievements in the history of human understanding. But the CMB isn't the only tool. Astronomers also studied the abundances of light elements in the oldest stars and gas clouds: hydrogen, deuterium, helium-3, helium-4, and lithium-7. Each of these elements was produced in specific quantities during Big Bang nucleosynthesis, and each serves as a probe of conditions in the first few minutes. Deuterium is particularly useful because it is only produced in the Big Bang, never in significant quantities by stars, and is slowly destroyed inside stars as it fuses with protons to form helium-3. The current abundance of deuterium in the universe is a lower bound on what was produced in the Big Bang. Measurements of deuterium in very distant, very ancient gas clouds, absorption systems in quasar spectra representing gas that has been as minimally processed as possible, reveal abundances that match theoretical predictions beautifully. This is one of the strongest confirmations of nucleosynthesis theory. Helium-4 is measured in ancient, low metallicity regions, gas clouds, and old stars that have had minimal contamination from stellar nucleosynthesis. The measured value of 24 to 25% by mass matches the prediction. Helium-3 is detected in our own galaxy's interstellar medium and in some planetary nebulae. And then there's Lithium-7, measured in the surfaces of the oldest and most metal-poor stars in the Milky Way, stars in the halo that formed from nearly pristine Big Bang material. The measurements give consistent values that are 3 to 4 times lower than predicted. The lithium problem is observed in the spectra of stars across many different research groups using many different instruments. It is one of the most carefully checked discrepancies in all of cosmology. Large particle accelerators like CERN's Large Hadron Collider can recreate conditions that existed in the first microseconds of the universe, allowing physicists to study quark-gluon plasma, to measure the properties of the particles that participated in nucleosynthesis, and to search for new physics beyond the Standard Model. The relativistic heavy ion collider at Brookhaven National Laboratory was the first facility to create and study quark-gluon plasma, finding that the plasma behaves more like a nearly perfect liquid than the weakly interacting gas theorists had expected. Another surprise, another revision of our understanding. The Bell experiment in Japan, the LHCb experiment at CERN, and other precision measurements study CP violation, the asymmetry between matter and antimatter, in the hope of finding larger violations than the Standard Model predicts, violations that might explain why the universe has atoms at all rather than a uniform bath of radiation. And gravitational wave detectors like LIGO and Virgo are opening a new window. Gravitational waves produced by inflation or by phase transitions in the early universe might be detectable as a background of gravitational radiation permeating all of space. If detected, such a background would be direct evidence of processes that occurred in the first fractions of a second, before the cosmic microwave background was produced. It would be an entirely new way of observing the ancient universe, and one that would confirm or refute specific models of inflation with data that presently we simply do not have. The story of the first atoms is also the story of us. Every hydrogen atom in a water molecule in your body has a proton at its center that has existed since the first second of the universe. That proton formed when the universe was a microsecond old and quarks combined into hadrons. It may have briefly met an antiproton and been annihilated and recreated several times during the first microsecond of furious particle-antiparticle chaos. But at some point, due to the matter-antimatter asymmetry we still don't fully understand, it became one of the surplus protons that survived the annihilation era. It has existed continuously ever since. That proton has lived through every chapter of cosmic history. It was present when the universe became transparent at 380,000 years. It floated through the ancient intergalactic medium during the cosmic dark ages, the hundreds of millions of years before the first stars formed. It may have been pulled by gravity into the halo of dark matter that eventually became one of the first galaxies. It may have been part of the gas cloud that collapsed into one of the very first stars, a vast and violent stellar giant that burned bright and died young. When that star exploded as a supernova, the proton was expelled back into the interstellar medium. Then it was gathered again into another molecular cloud, another star, perhaps many stars, over billions of years. Each time the same proton, pulled by gravity, compressed and heated, participating in the nuclear reactions around it, but surviving as hydrogen, uncaptured in any helium nucleus, cycling through the cosmic ecosystem of birth and death and dispersal that characterizes the life of matter in a galaxy. Eventually, about 5 billion years ago, a molecular cloud in an outer arm of the Milky Way began to collapse. In its center, a new star ignited, our Sun. Around it, a disk of gas and dust began to coagulate into planets. One of those planets, the third from the star, was rocky and warm and would eventually develop oceans. And in those oceans, the chemistry of life began. That proton has been in countless water molecules. It has been in the ocean, it has been in the rain, it has been inside a bacterium, a fish, a fern, a dinosaur. It has cycled through the atmosphere as water vapor and fallen as rain and soaked into the soil and been drawn up through the roots of a tree and breathed out again as transpiration. It has participated in photosynthesis, in cellular respiration, in every metabolic reaction that has ever occurred in every living thing on Earth that ever drank water. And now it is here, in you, part of a water molecule or a protein or a fat molecule or the fluid filling a cell, participating in the chemistry of life. Surrounded by structures of atoms so complex that they can think about where atoms come from. Every oxygen atom you breathe was forged inside a star that lived and died before the sun was born, scattered into the interstellar medium by its explosive death, gathered into the molecular cloud from which our solar system condensed, and eventually incorporated into the atmosphere and the oceans, and ultimately into you. The carbon in your DNA was assembled in the helium-burning cores of red giant stars, expelled in stellar winds over millions of years, mixed into the interstellar gas, and swept up in the formation of Earth. The iron in your hemoglobin was synthesized in the cores of massive stars during their final stages of nuclear burning, or forged in the violent merger of two neutron stars and scattered through the galaxy when those stars met their end. We are, in a very literal sense, made of the universe. Our atoms are ancient. They carry no information about their history. They don't remember being part of a nebula or a star or a dinosaur. But the history happened. The atoms existed through all of it. Carl Sagan famously said that we are made of star stuff. He was right, but it's more than that. The hydrogen in us is not star stuff, it's Big Bang stuff. The most ancient matter there is. Older than every star, older than every galaxy, older than every structure in the universe. The proton is as old as time itself, very nearly, and it has been here, in one form or another, for every moment of cosmic history that has followed. The first atoms were forged in conditions so extreme that we can barely describe them. They were distributed through the universe by processes we are still working to understand. They were shaped into structure by dark matter whose nature we haven't identified. They were lit up as stars by gravitational collapse that followed templates laid down by quantum fluctuations during inflation. and they eventually became complex enough, assembled into molecules intricate enough to produce things that can look up at the sky and ask where they came from. That is perhaps the deepest astonishment of all. The first atoms are now, billions of years later, in some places arranged into beings that are trying to figure out what the first atoms were. The universe, through us, is asking questions about its own origin. So what happens next? Where does the science go from here? The James Webb Space Telescope is currently peering deeper into the past than any instrument before it. It is observing the first galaxies that formed from the first atoms, studying their composition, their structure, their star formation history. It is looking for the signatures of population 3 stars, the very first generation of stars that formed from pure hydrogen and helium, before any heavy elements existed. These stars have never been directly observed. They were enormous and brief and violent, living fast and dying as supernovae that seeded the universe with the first heavy elements. Webb may find their signatures in the spectra of very early galaxies. Already, Webb has surprised scientists. It has discovered that galaxies in the very early universe, at redshifts of 8, 10, 12 and beyond, representing times when the universe was less than 1 billion years old, are more massive, more structured and more numerous than models predicted. The early universe appears to have formed galaxies faster than our best simulations of galaxy formation suggested it should. Some astronomers are proposing revisions to how dark matter behaves on small scales. Others are questioning whether the physics of star formation in primitive, metal-free conditions is correctly modeled. The first atoms in the first galaxies are already revising our understanding of how structure grew. The Euclid satellite, launched in 2023, is mapping the large-scale structure of the universe across billions of light years, providing new constraints on dark energy and dark matter, and testing whether the standard cosmological model, born from the study of the first atoms, holds up when examined on the largest scales. The CMB Stage 4 experiment, a proposed ground-based telescope array, would measure the polarization of the cosmic microwave background with sufficient precision to detect the gravitational wave background left by inflation. If that background is detected, it would be the most direct evidence of inflation ever obtained, confirming the scenario that explains why the first atoms emerged into a smooth, flat, monopole-free universe. If it is not detected, many models of inflation would be ruled out, forcing a major revision. The Deep Underground Neutrino experiment, currently being built in the United States, will study neutrino properties with unprecedented precision. Neutrinos played a crucial role in Big Bang nucleosynthesis, determining the neutron-to-proton ratio at the moment they decoupled, setting the eventual helium abundance. Precise measurements of neutrino masses and mixing angles help constrain nucleosynthesis models. And if the experiment detects leptonic CP violation, the asymmetry between neutrinos and antineutrinos, it would provide crucial evidence for whether the matter-antimatter asymmetry of the universe could have been generated in the lepton sector and then transferred to baryons. And the long search continues for direct detection of dark matter. Experiments buried underground to shield them from cosmic rays. Experiments looking for dark matter particles annihilating in the galactic center or the sun. Experiments at the LHC searching for new particles that could be dark matter candidates. So far, nothing conclusive. But the searches continue, becoming more sensitive with every generation of experiment. Lux Zeppelin, currently the most sensitive direct detection experiment ever operated, has found nothing, ruling out large swaths of parameter space for WIMP dark matter. Some physicists take this as evidence that dark matter is not WIMPs and is something altogether different. Others argue that WIMPs could still exist at properties not yet reached by current experiments. The lithium problem remains unsolved. New measurements of stellar lithium abundances in the oldest stars are being made with increasingly powerful spectrographs. New calculations of nuclear reaction rates in Big Bang Nucleosynthesis are being performed with more precise nuclear physics inputs. And theorists continue to explore whether new physics might provide a solution. There is also what cosmologists call the Hubble tension. Different methods of measuring the current expansion rate of the universe give different answers. Measurements based on the cosmic microwave background and early universe physics give one value for the Hubble constant. Measurements based on the local universe, using Cepheid variable stars and Type 1. A supernova way to measure distances give a value that is roughly 5 to 10% higher. The discrepancy is now statistically significant. Either there is a systematic error in one or both measurement techniques, or there is new physics in the early or late universe that current models don't include. Either possibility is important. If it's new physics, it may involve the behavior of dark energy, or dark matter, or even the physics of the first atoms themselves during nucleosynthesis. The universe keeps surprising us. The first atoms keep revealing new secrets. The matter-antimatter asymmetry remains one of the deepest unsolved problems in physics. Experiments searching for CP violation in additional systems, including in neutrinos, may provide clues. The T2K experiment in Japan and the NOVA experiment in the United States are both measuring whether neutrinos and antineutrinos behave differently, a form of leptonic CP violation that could potentially be connected to the matter-antimatter asymmetry of the universe. If leptonic CP violation is large enough, it could have driven a process called leptogenesis, in which an asymmetry in the lepton sector in the very early universe was subsequently converted into a baryon asymmetry. The atoms that exist today could ultimately trace their existence to an asymmetry in neutrino behavior. We don't yet know whether this is true. Measuring neutrino CP violation is extraordinarily difficult. The experiments are just beginning. There is something deeply humbling about studying the first atoms. Scientists built sophisticated theories and mathematical models. They calculated precisely what should have happened in the first 3 minutes of the universe. They made quantitative predictions about the abundances of hydrogen, helium, deuterium, and lithium. Predictions that could in principle be confirmed or refuted by observation. And the observations came in, and the big picture matched, and everyone felt good about understanding something fundamental. And then the details started coming in. The lithium was wrong by a factor of 3. Dark matter had to exist to explain the structure that formed from those first atoms, and dark matter is unknown. Dark energy had to exist to explain the expansion history, and dark energy is unknown. The matter-antimatter asymmetry that allowed atoms to exist at all is larger than the Standard Model can explain. The inflation that smoothed the universe for the atoms to spread into is unconfirmed. The proton that forms the core of every hydrogen atom might be unstable on timescales far beyond any measurement we've made. 7 ways that the full story of the first atoms exceeds our understanding. 7 places where the universe has told us that our models, however successful they are at describing the basic picture, are incomplete. And that's how science works. Not the neat confirmation of a theory and then moving on, but the confirmation of the broad strokes followed by the discovery that every specific detail is more complicated, more strange, more interesting than the model allowed. The universe is always more sophisticated than we are. The first atoms are among the most studied objects in science. Hundreds of experiments, thousands of papers, decades of theoretical development, and we still don't fully understand them. We still can't explain why they exist in preference to antimatter. We still can't explain the lithium. We still don't know what the dark matter is that sculpted them into structure. We still don't understand the dark energy that is now slowly diluting them across an ever larger universe. This is the nature of science at the frontier. Every answer opens new questions. Every measurement reveals new puzzles. Every confirmation of the broad picture exposes new mysteries in the details. And the atoms themselves don't know any of this. They don't know they're ancient. They don't know they survived annihilation by a narrow margin of 1 in a billion. They don't know they were sculpted by invisible dark matter. They don't know the universe they inhabit is accelerating toward a cold, thin death driven by a mysterious energy no one understands. But we know. Or rather, we are learning. In the only atoms we know of that are capable of asking such questions. The proton at the core of a hydrogen atom in your body has existed for 13.8 billion years. It survived conditions so extreme that time itself barely had meaning. It formed from quarks in the first microsecond. It almost annihilated against an antiproton, but didn't because of an asymmetry we don't understand. It survived the first 3 minutes as protons and neutrons fused into helium all around it, but it ended up in hydrogen, uncaptured. It floated through the universe as a bare proton for 380,000 years, until the universe finally cooled enough for it to capture an electron and become a proper atom. Then it spent billions of years in the interstellar medium, occasionally being incorporated into stars and expelled again, occasionally participating in chemical reactions as part of molecular hydrogen or water or organic molecules. It survived the violent early history of the solar system, swept up in the accretion of the proto-Earth, dissolved in the oceans, cycled through the atmosphere, incorporated into living cells, and released again, over and over through billions of years of Earth's biological history. And now it is here, in you, part of a water molecule or a protein or a fat molecule or the fluid filling a cell, participating in the chemistry of life, surrounded by structures of atoms so complex that they can think about where atoms come from. The universe baked its first atoms in the first 3 minutes. It has spent 13.8 billion years using those atoms to build things. And among the most remarkable things it has built are beings capable of discovering the story of those first 3 minutes. That, perhaps, is the most ancient secret of the first atoms. not just how they formed, but what they eventually became. Tonight, we explored the shocking discoveries science has made about the first atoms. The hydrogen and helium forged in the first 3 minutes of the universe, distributed through the cosmos by processes we are still working to understand, shaped into structure by invisible dark matter, sculpted into galaxies and stars by gravity-following templates set by quantum fluctuations stretched across the sky by inflation. We started where the story begins, 13.8 billion years ago, in the first microsecond of the universe, when quarks combined into protons and neutrons. We traced the universe's temperature falling from effectively infinite through the phase transitions that produced hadrons, through the first second when neutrino decoupling locked in the ratio of protons to neutrons, and into the extraordinary 3 minutes of Big Bang Nucleosynthesis, when that ratio determined the composition of everything. We learned that the basic prediction of Big Bang Nucleosynthesis was spectacularly confirmed. Roughly 75% hydrogen and 25% helium by mass, exactly as the math demanded. One of the great predictions of scientific theory, confirmed by observations of the oldest gas clouds and most primitive stars in the universe, and confirmed again by the cosmic microwave background, whose power spectrum encodes the same physical parameters independently and agrees with extraordinary precision. And then we learned about the 7 ways the universe exceeded our understanding. The lithium problem. The factor of 3 discrepancy between predicted and observed lithium-7 that has resisted explanation for decades and remains the most puzzling open question in Big Bang nucleosynthesis. Something is wrong with our prediction, or something about the oldest stars we use to measure it, or some new physics we haven't discovered yet. Probably one of those 3 things. We don't know which. Baryogenesis, the mysterious asymmetry between matter and antimatter that allowed atoms to exist at all, an asymmetry 10 billion times larger than our best theory can explain. Without this asymmetry, the universe would be an eternal sea of cooling photons. Everything that exists, every atom of you and every star in the sky, and every galaxy in the cosmos, exists because of a 1 in a billion advantage that matter had over antimatter in the first second of time. We don't know why. Dark matter, which shaped where the first atoms ended up. 5 times more dark matter than ordinary matter. Invisible, undetected in any laboratory, governing the gravitational skeleton of every galaxy. Unknown in its fundamental nature despite decades of searching. Dark energy, which now drives the accelerating expansion of the universe, diluting those first atoms across an ever larger volume, pushing the universe toward a cold, dark, lonely future. 68% of the total energy content of the universe, completely mysterious. The worst prediction in the history of physics when we try to calculate it from first principles. Cosmic inflation, which solved the monopole problem and prepared the stage for nucleosynthesis and structure formation. Possibly the most important event in the first second of the universe, and potentially unconfirmed, still awaiting the decisive observational test that will tell us whether it really happened. The extraordinary stability of the proton, the ancient core of the first hydrogen atom, persisting unchanged since the first second, stable for longer than any measurement has been able to test, and possibly not perfectly stable, possibly subject to decay on time scales that make the age of the universe look like an instant, in ways that would eventually erase all ordinary matter from the universe. And the multiverse, the deepest and most uncomfortable implication of all. That the universe we inhabit, with its particular physical constants that permit atoms and chemistry and stars and life, may be one of an infinite number of bubble universes embedded in an eternally inflating metaspace. That the apparent fine-tuning of physics for the existence of atoms may be an illusion, an observer selection effect in a space of infinite possibilities. An idea that may be profoundly true and may be, by some definitions, unprovable. 7 discoveries. 7 ways the universe exceeded our models. 7 places where the ancient story of the first atoms reaches beyond what we currently understand. The science of the first atoms is about more than cosmology. It connects to everything. It connects to particle physics, because the particles that participated in nucleosynthesis and in baryogenesis are studied at the LHC and at precision experiments around the world. It connects to nuclear physics, because the reactions of nucleosynthesis involve nuclear cross-sections that must be measured in the laboratory. It connects to astrophysics, because the abundances of the first atoms are measured in stars and gas clouds and inform our understanding of stellar evolution. It connects to gravitational physics, because dark matter and dark energy reveal that our theory of gravity, even Einstein's general relativity, may need modification or extension. And it connects to philosophy, because the question of why the physical constants have the values they do, values that permit the existence of atoms at all, reaches beyond what empirical science alone can answer. The cosmic microwave background is out there right now. Every radio antenna on Earth picks up a tiny fraction of it. It fills the entire sky in every direction. It is the afterglow of the fireball in which the first atoms formed. It is, literally, the oldest light in the universe. When you hear static on an old radio, some fraction of that hiss comes from photons that last scattered off plasma 380,000 years after the Big Bang, and have been traveling uninterrupted through the expanding universe ever since. Ancient light turned to microwave noise, filling the cosmos. And somewhere in that ancient light, in the precise pattern of its temperature fluctuations, in the exact shape of its power spectrum, in the tiny polarization patterns imprinted on it by the physics of the early universe, in the B-mode polarization that inflation's gravitational wave background would leave like a fingerprint on the oldest light, are answers to questions we haven't figured out how to ask yet. The first atoms are still teaching us, still surprising us, still showing us that the universe is more elaborate, more subtle, and more astonishing than any theory we have built to describe it. The proton has existed for 13.8 billion years. It will likely exist for many orders of magnitude longer, long after the sun has burned out, long after the Milky Way has merged with Andromeda and the combined galaxy has scattered into a vast, diffuse cloud, long after the last stars have exhausted their fuel and gone cold and dark, long into the black hole era, when the universe's matter is concentrated into black holes that themselves slowly evaporate over incomprehensibly long timescales. The proton will be there, unless, of course, proton decay is real. In that case, every proton in the universe will eventually vanish. Every hydrogen atom will cease to exist. The first atoms, the most ancient objects in the cosmos, will disappear. The universe's long experiment with ordinary matter will come to an end. But not yet. Not for a very long time. Long enough for us to be here, to look up, to wonder, and to ask where we came from. The universe baked the first atoms in 3 minutes. It has spent 13.8 billion years using those atoms to build things. It built galaxies and stars and planets. It built chemistry and biology. It built creatures capable of measuring ancient starlight, of detecting cosmic microwave radiation, of calculating what happened in the first second of time, of discovering that matter and antimatter should have been equal but weren't, of finding that 95% of the universe is made of things they cannot identify. And among the most remarkable things those creatures have discovered is this: the first atoms, the simplest and oldest matter in existence, are still full of secrets. We have barely begun to understand them. The universe baked the first atoms in 3 minutes. It will take us much longer to understand what it did and why, but we're working on it. And the first atoms, patient beyond all imagining, are waiting to reveal what they know.